9 miles, that's all that separates Europe from Africa. 9 miles of open water. You could kayak it. People have swum it. So why, after over 100 years of trying, has no one been able to connect these two continents? The answer isn't distance. It's not money. It's not even politics. It's the fact that this tiny strip of ocean might be one of the most geologically violent, ecologically critical, and engineering-defying places on the entire surface of the Earth. Imagine waking up in Madrid, Spain, hopping on a train and arriving in Marrakech, Morocco in under 2 hours. No flight, no passport line on a ferry, no rough Atlantic crossing, just a train ride between continents. That's the promise of the Gibraltar Tunnel, a project so ambitious, so dangerous to build, and so potentially transformative that engineers, governments, and dreamers have been arguing about it since 1930. But here's the thing, nobody tells you in the headline. Building any structure across the Strait of Gibraltar isn't just difficult. It may be the single hardest engineering challenge humanity has ever seriously attempted. And right now, for the first time in history, we might actually be close to doing it. In this video, we're going to break down exactly why this strait is so dangerous, why a bridge is completely off the table, how this tunnel is actually designed to survive earthquakes and crushing pressure, and what it would mean for two entire continents if it ever gets built. Stay with me, because this story goes deep, literally. To understand why this is so hard, you first need to understand what the Strait of Gibraltar actually is. On the surface, it looks deceptively simple. A narrow channel, some waves, a little wind, but underneath that calm surface, it's a different world entirely. First, the depth. The strait drops to around 3,000 feet at its deepest point. That's nearly 3 times the height of the Eiffel Tower straight down. This isn't shallow coastal water. This is a dark, pressurized abyss. Second, the currents. The Strait of Gibraltar is where the Atlantic Ocean meets the Mediterranean Sea, and because the Mediterranean evaporates faster than it refills, there's a constant, powerful flow of Atlantic water rushing inward near the surface, while a separate, denser, saltier current flows outward underneath it. 2 rivers moving in opposite directions at the same time. Invisibly, for ships, this is manageable. For engineers trying to plant foundations on the seabed, it's a nightmare. But the third factor, this is the one that changes everything. The Strait of Gibraltar sits almost exactly on the boundary between the African tectonic plate and the Eurasian tectonic plate. These 2 massive slabs of the Earth's crust are constantly grinding against each other, slowly, just millimeters per year, but relentlessly. And that movement doesn't just cause earthquakes. It means that whatever you build here must survive constant, never-ending ground shift for potentially hundreds of years. In 1755, an earthquake originating near this region triggered a tsunami that destroyed Lisbon, Portugal, and killed tens of thousands of people. The geology here doesn't forgive mistakes. So the first idea most people have is, why not just build a bridge? 9 miles. Engineers build long bridges all the time. The Danyang Kunshan Grand Bridge in China stretches over 100 miles. The bridge tunnel across the Chesapeake Bay in the U.S. is nearly 20. So what's the problem? 3 massive problems. Problem 1, depth and foundations. To build a bridge, you need foundations anchored to the seafloor, but the seafloor here is nearly 3,000 feet down, sitting on unstable, earthquake-prone ground. Building stable bridge pylons at that depth, in those currents, on that geology, the engineering doesn't exist yet to do it safely. Problem 2, shipping lanes. The Strait of Gibraltar is one of the busiest shipping corridors on Earth. Over 300 ships pass through every single day. A bridge would need to be high enough and clear enough to never interfere with international shipping traffic. The clearance requirements alone would make the structure almost impossibly tall and expensive. Problem 3, the ecosystem. This one surprises people. The Strait's unique double-layer current system isn't just a quirk of geography, it's the lifeblood of the Mediterranean Sea's entire food chain. The Atlantic water that flows in carries oxygen and nutrients. The outflow carries salt back to the Atlantic. Massive bridge foundations on the seafloor would disrupt this circulation. Marine biologists have warned that the ecological damage could ripple across the entire Mediterranean, affecting fisheries, biodiversity, and coastal communities across 20 countries. So, no bridge. The answer, it turns out, has to go under the problem entirely. The idea of a tunnel under the Strait of Gibraltar was first formally proposed in 1930. back when tunnel boring technology was in its infancy and the project was essentially a dream on paper. But in 2003, Spain and Morocco signed an agreement to restart serious feasibility studies. Engineers began drilling test bore holes. Geologists mapped the seafloor in detail. And by the mid-2020s, plans had advanced to the point where construction could potentially begin around 2030. So what exactly are they planning to build? The Gibraltar Tunnel, as currently designed, would stretch approximately 25 miles, about double the length of the Channel Tunnel connecting England and France. It would consist of 3 separate bored tunnels, 2 main rail tunnels running in opposite directions, and a central service and safety tunnel between them. The same configuration used in the Channel Tunnel and proven to work. But here's where Gibraltar becomes a completely different beast. The Channel Tunnel's deepest point sits about 250 feet below the seabed. The Gibraltar Tunnel, at its lowest point, would run more than 1,000 feet below sea level. That's not a modest upgrade. That's a fundamentally different engineering environment with a water pressure, geological complexity, and construction challenges that dwarf anything attempted before. The tunnels would be bored using massive tunnel boring machines, essentially giant mechanical worms that grind through rock, simultaneously installing reinforced concrete lining segments behind them. Modern TBMs can handle incredibly hard rock, but the Gibraltar crossing presents a unique geological challenge. The tunnel must pass through multiple different rock types, some soft and unstable, some fractured by ancient fault lines. Then there's the earthquake problem. The tunnel can't be rigid. A completely inflexible structure in seismic terrain would eventually crack and fail. Instead, engineers are designing a system that can actually move with flexible joints at regular intervals that allow the tunnel to absorb ground shifts and seismic waves without breaking. Think of it less like a solid pipe and more like a segmented spine designed to bend without snapping. If construction begins around 2030 and takes the estimated 10 years to complete, we could be looking at a working tunnel somewhere around 2040. Now here's where this stops being just an engineering story and becomes something much bigger. A completed Gibraltar Tunnel would allow trains to travel between Europe and Africa in approximately 30 minutes. Passengers, cargo, and freight that currently rely on ferries, which are weather-dependent and limited in capacity, could move continuously day and night in all conditions. Projections suggest the tunnel could carry millions of passengers per year, while simultaneously transforming trade flows between Europe and sub-Saharan Africa, a combined market of over 1.5 billion people. Morocco, already a growing manufacturing hub, would become directly connected to the European rail network. Spanish and Portuguese ports would gain fast land routes into Africa. The economic ripple effect, investment, tourism, logistics could reshape the economic geography of 2 entire continents. And there's a human dimension that goes beyond economics. The Strait of Gibraltar is currently one of the most dangerous migration crossings in the world. Thousands of people risk their lives every year attempting to cross in small boats. A legal, accessible land connection between continents is part of a much larger geopolitical conversation about mobility, dignity, and the relationship between Europe and Africa. Skeptics point out, and fairly, that this has been almost happening since 1930. So is this real, or is it just the world's longest-running engineering fantasy? To answer that, look at the precedents. The Channel Tunnel, completed in 1994, was considered impossible by many until the moment it opened. It runs 31 miles. It reaches 250 feet below the seabed and today carries over 10 million passengers per year. It transformed the economic and cultural relationship between Britain and mainland Europe almost overnight. The Eurasia Tunnel in Istanbul, completed in 2016, bores directly under the Bosphorus Strait, connecting Europe and Asia beneath one of the world's busiest waterways in a seismically active region. It was finished on time. It works perfectly. And Istanbul sits on geology that in some ways is comparable to Gibraltar. Both of these projects were called impossible. Both were completed. Both changed their regions permanently. The Gibraltar Tunnel is harder, significantly harder. But the engineering playbook now exists in a way it simply didn't in 1930 or even in 1990. Of course, once engineers start talking about tunneling under the Strait of Gibraltar, someone always asks the next question: what about the Atlantic Ocean? A transatlantic tunnel connecting North America and Europe has been discussed, mostly by futurists and science fiction writers, for over a century. The concept is seductive. A vacuum tube or submerged floating tunnel running 3,500 miles across the Atlantic at depths of up to 27,000 feet. The physics could theoretically work. The engineering? We are generations away, at minimum. The pressure at those depths would be almost incomprehensible. The cost would dwarf the GDP of most nations, and the geological instability across the mid-Atlantic ridge makes the Gibraltar crossing look simple by comparison. For now, transatlantic tunnels live where they belong, in the realm of imagination. And that's okay, because the greatest engineering projects in history always started in imagination. The Channel Tunnel was once imagination. The Eurasia Tunnel was once imagination. And 30 years from now, the Gibraltar Tunnel might just be a Tuesday morning commute, 9 miles, separated for all of human history. 2 continents, 2 cultures, 2 worlds, staring at each other across a strip of churning water that has defined the edge of the known world since the ancient Greeks called it the Pillars of Hercules. If the Gibraltar Tunnel gets built, and right now, for the first time, that's a real if rather than an impossible one, it won't just be an engineering achievement. It will be a statement that the barriers we think are permanent aren't. If you made it this far, I want to know one thing from you. Drop it in the comments right now. Do you think the Gibraltar Tunnel will actually be built by 2040, or will it stay a dream forever? I read every single comment, and I genuinely want to know what you think. If you want to go deeper on impossible engineering projects, the tunnels, the megastructures, the ideas that shouldn't work but do, make sure you're subscribed and hit the notification bell. We cover this kind of thing every day. And if you want to keep watching right now, the video on how the Channel Tunnel was actually built and almost wasn't is right here. It's a story involving collapsed tunnels, political collapse, and one of the most dramatic engineering rescues in history. So see you there.